Okay, so let's now take this commutator and sandwich it between the initial and final states. So we are going to get this n prime, l prime, m prime, and then commutator of L squared, okay, and L squared. Let me just write it as Z, but this will be true for any component, X, Y, or Z, okay. And on the right, I have N, L, M, and what, 2 H bar, and then expectation N prime, L prime, M prime, Z, L squared minus L squared Z, N, L, M. Okay, so we have this huge expression. So what does this do? This is going to give me n prime, l prime, m prime, and then l squared, okay, l squared z minus l squared z l squared and n l m. So let me work out the left hand side first, and then we'll look at the other side. So L squared working towards the left, operating to the right, is going to give me what? H bar squared, right? And L prime plus 1, okay, is the eigenvalue that I get from that. And for this one, I'm going to get minus L plus 1, right? And I still have rest of the object, okay? So I still have over here n prime, L prime, m prime, and L squared z, n, L, m. Okay, but this is again something relatively simple, L squared z minus z L squared. Okay, so this is going to give me another factor of h bar squared, L prime plus 1 minus L plus 1, okay, multiplied by this, okay, B Z A. So the whole left-hand side becomes h bar to the 4, okay, this L prime plus 1 minus L plus 1 squared, okay, times that, okay, but let me just move the right-hand side to the left, okay, so the right-hand side is going to be 2 h bar, just h bar, that should be h bar squared, right? Otherwise I don't have good units. Okay, so 2 h bar squared, and then I have this operating to the right gives me L plus 1. I'm writing things which are not correct. Why are not you stopping me? This is not a commutator, so it's plus 1. Okay, so it's going to be plus L prime plus 1. Okay, and h bar squared. Okay, so all of the h bars cancel. And this is still being multiplied by B Z A. Okay, is equal to 0. So I moved everything to the left-hand side. So this again, you see, is a selection rule for these L's. Okay, so if this is not going to be 0, I need to have this thing equal to 0. Okay, and okay, unfortunately, this is also not so simple to simplify because you see these are second power of L squared, so fourth power of L. But things do simplify quite a bit if you go to a different set of variables. So if you just say, for example, L plus is equal to L plus L prime plus 1, and L minus is equal to L minus L prime, or is it the other way around? Well, it doesn't really matter. Okay, so if I have something like this and use these instead of those, so what does that mean? I really have to solve these things for L and L prime. So you see L prime I can obtain by just adding these two and subtracting 1 and divide by 2. So it's 1 over 2. Add these things together, L plus L minus. So the L's cancel, but I have 2L prime plus 1. So let me subtract that 1, and that's what I have. And L is the other way around. I have to subtract this from that, right? So I'm going to get 1 over 2 L plus minus L minus. Okay, but I still have a 1, right? So I still have to subtract minus 1 and divide by 2. Okay, so you can check these things are correct. Yes. Okay, so now we just go ahead and, okay, perhaps I'll erase it. I'll just go on with the algebra to see how much time it takes. If it takes too much time, again, I'm going to just write down the result. All right, so let's now write that equation in. So I have L prime and L prime plus 1. So I'm just going to write this, well, maybe I'll write it here so that it's obvious what I'm doing. So L prime plus 1 minus L plus 1, okay, squared. Minus 2 L plus 1 plus L prime plus 1, okay, and I want that to be equal to 0. So L prime, in place of L prime, I'm going to put in, okay, that thing. So there will be a number of factors of 1/2. So each term here, each L here is going to bring in 1/2. So that's going to be 1/4, and then when squared, it's going to 1 over 16. Okay, and in place of L prime, I'm going to put in L plus L minus minus 1, and L plus 1 is going to be L prime plus 1 is going to be L plus L minus plus 1, right? If I add 1 to L prime, it just makes this a plus 1. Then I have a... We
also had minus 1, we just cancel with the plus 1.
Again?
So we also had plus 1 in L prime plus 1.
Yeah, but when you add L plus 1,
Okay,
it just makes it plus 1, okay? So we are okay. Okay, so for this one, I have basically the same thing with minus in between. L plus minus L minus minus 1 and L plus minus L minus plus 1. Okay, so those are that. The square of this minus 2, okay, same stuff, L plus, yeah, let me write in the same order, L plus L minus 1, L plus L minus plus 1 plus L plus minus L minus 1, L plus minus L minus plus 1. Okay, so let's just see what we have here. So this is this two together is going to give me L plus L minus squared minus 1, right? Minus the second term, which is L plus minus L minus squared minus 1. Okay. So all of this 1 over 16 and squared. So these minus 1s cancel. Okay, so I again have these squares. I have to remember how this goes. Let's also work out the other side. Oh, I forgot the factors of 1/2 here. So here I have 1/2 from that, 1/2 from that. So this is 1 over 4. Okay, so minus 1/2. Same sort of stuff. L plus L minus squared minus 1 plus L plus minus L minus squared minus 1. Okay, so L plus, what does that give me? The cross terms go away. Okay, so let's go see. 1 over 2 L plus squared plus L minus squared. The cross terms cancel. Minus 1, right? And there's a factor 2. Okay, I get L plus squares from both, L minus squares from the others, so that's what I get. What about this guy here? So that's difference of 2 squares, so that's going to be 1 over 16. So I add and subtract these things. So when I so this is of the form a squared minus b squared, right? So I want to write this as a plus b times a minus b. So a plus b is going to be 2l plus squared, right? And a minus b squared is going to be 2l minus squared. Okay, so all of that squared. Okay, so where are we? So let's look at the constants. 2 times 2 is 4, squared is 16, so that goes away. So this is L plus to the 4th, L minus to the 4th, minus L plus squared minus L minus squared plus 1, right? And I can write this as, okay, L plus squared minus 1, L minus squared minus 1, right? So what does this say? This says, okay, so this has to be equal to 0. So I need to have these things, at least one of these things equal to 0. If, okay, so this thing has to be equal to 0 if yeah, matrix element, where's the matrix element? Yeah, okay, B, Z, A is not equal to 0. So what are these conditions? So either this has to be 0, which is L prime plus L plus 1, okay, squared. So either this has to be 0, okay, or I need to have L minus L prime equal to 0. No. I'm putting in the wrong things, right? No, that's okay. I'll press. Oh. Not so confused. L minus. No, yeah. Okay, so this is what. This is equal to. Okay, so. L plus squared, which is this thing is equal to 1, right? Or L minus squared, which is this, okay, is equal to 1. Okay, so now let's see. Why?
Because we have L plus to the power 4 times L minus to the power 4 in the left hand side, but in the right hand side we have L plus squared.
Oh, yes.
And L minus squared.
You are right. Let's see. L squared. So I made a mistake someplace.
In the previous step, we put an extra square on both terms. There is only one square.
Oh, yes. A plus B times A minus B. Thank you. So we'll get straight somehow. Okay. So now let's just analyze these things. Okay. So this one says, okay, you can have delta L equal to 1. All right. And then delta L is equal to plus or minus 1. So that's one possibility. This one says, okay, the only way this can be equal to 1 is if L prime equals 0. Okay. So, but on the other hand, this is a special case. Okay, so you see, if you look at the logic of this statement, this says if this is not going to be equal to 0, this has to be 0. It doesn't say if this is 0, this has to be non-zero, right? So it's possible that this is 0 and that is 0. And it turns out that this L equal to L prime equal to 0 case corresponds to this PZA equal to 0 anyway. Okay, so but in this special case, if I have n 0 0 z n 0 0, okay, so that corresponds, if L is 0, M has to be 0, right? So this thing is 0. Okay, this is some argument that you went through millions of times, but maybe I'll do it 1 million first time. So this is just y 0 0 star y 0 0, okay, and then you have this z, which is a cosine theta factor d omega, and we saw that this is equal to 0. So this case is not meaningful. Okay, so this doesn't count because the corresponding matrix element is 0 anyway. So the proper case is just delta L has to be equal to plus or minus 1. Okay, so for this dipole type transition, the type of transition in which we have the expectation value of z equal to be non-zero, we have those three conditions that we have seen. Okay, so let me put that in a box also. So delta L must be equal to plus or minus 1. And then the M object can be 0 or plus or minus 1. Okay, so you can make a picture of what transitions are allowed. For example, for the hydrogen atom, let's see what we are going to get. Okay, so we have the ground state, which corresponds to n equal to 0, L equal to 0, and M equal to 0. Okay. The excited states, we have a number of them. Okay, so we have n equal to 1, and okay, so L equal to, okay, so let's just put these things as, what's the best way? So I'll put NLM. This is, so I'm sorry, this is 1. First excited state is 2 0 0, or 2 1 minus 1. Let's see, maybe it's just best to put the L on the top or something. Okay, so this is going to be the L equal to 0, L equal to 1 state, and so on. So I have an L equal to 1 state here, which is permissible. And excuse me, and then I have 3 0 0. Well, okay, these are the end states. So n equal to 1, n equal to 2, n equal to 3 state, L equal to 0, L equal to 1, L equal to 2. Okay, and there's in addition M, but the diagram will be too cluttered if we do that. Okay, so I cannot have a transition, for example, from n equal to 2, L equal to 0 state to the ground state. Okay, but I can have a transition. Okay, I can have transitions between these two states because it corresponds to delta L equal to 1. So I can have all these types of transitions, okay, from one state to another, which goes like that. Not only those, but of course I could also have jumps from, okay, jumps in 2 steps. I can go from that energy state to that one. But I cannot have, for example, a transition from this one to that one because that corresponds to a delta L equal to 2. And in each one of these transitions, I also have to be aware of the magnetic quantum number m also. Okay, so for example, the transition between this point and that point is called a forbidden transition. Okay, so these forbidden transitions are interesting and sometimes useful, because if you can get the particle into that state by some route, it will have a long lifetime. Okay, because the transition rate to the you are not going to have a transition dipole transition from one state to the other. Okay, but if you look at the forbidden transitions, if we go back to our picture of the electromagnetic wave and the atom, okay, so we had this electromagnetic wave, which we, now said polarized in some direction n now, and we just used a cosine omega t type of behavior, okay, at any point. But we really should have used something which looks like E0 and, okay, some k dot r minus omega t, right, with a cosine function. Okay, so we should really use for the electromagnetic wave, which goes something like that. Now, okay, so our atom is here, so we can put the origin over there, and the size of the atom r is so small that we neglected this first term. But now we can make an expansion around small r, so this is going to be E0 n cosine omega t when r is 0. But for small r, okay, if we make a Taylor expansion, we are going to get what? Minus sine k dot r. I'm sorry, we put k dot r equal to 0. So this is going to be k dot r sine omega t, right? So if I just expand this in a Taylor expansion for small k dot r, that's what I'm going to get, right? Omega t will be 0. Then I just differentiate with respect to k dot r, then I get this sine term, sine minus omega t, so it's going to be plus. Okay, so that's now the excuse me, a better representation of the field near the atom. So my expectation value for E dot r, excuse me, is now going to be equal to this E0 expectation value b, and I have this n dot r, which is the term that we have been working with all this time, times this cosine omega t factor. But now there's going to be an additional term, which is going to be n dot r times k dot r sine omega t. All right, and the right hand side ket. All right, so I have that now. For the forbidden transition, we see that this is 0, okay, if it is forbidden. But then this term, which is higher order, is going to be finite, possibly. Okay, so this now gives you a rate for the for this forbidden transition, which is not going to be 0, but it will have, of course, because this is much smaller term. You see I have a k dot r here. Again, k dot r means I have 2 pi over lambda for k, and r is the size of the atom, right? So this is a very small quantity. R is of the order of angstroms. This is of the order of hundreds of nanometers or something like that. Okay, so it's going to be a very small factor, but this now does not obey the selection rules that we have derived, because we derived the selection rule for something which looks like R. This has 2 factors of R in it. Okay, so this will result in a different type of transition. Okay, any questions? All right. So let me very quickly discuss, 15 minutes, okay, very quickly discuss with you the Einstein A and B coefficients. And that will be okay, so in the early days of quantum mechanics, or in fact we should say before quantum mechanics sort of started, black body radiation was an important problem that needed to be solved. Okay, so the Einstein analyze the problem. So this is, we are going to mix Einstein's approach and some amount of quantum mechanics to see what's going on, but it's of course quite amazing that Einstein could do this, a great deal of this before quantum mechanics. All right, so the problem is the following. We are going to take a black body object which corresponds to, okay, a cavity. So what we have inside this cavity at some certain temperature T is going to correspond to what's known as black body radiation. Okay, and then we will study the effect of what is happening to 2-level atoms inside this, okay, inside this box. So they are interacting with this thermal bath of photons, and that means some of them will be excited to the upper energy level, some of them will be in the lower energy level. And we know from statistical physics that the energy is going to be e to the minus energy difference, or kT, will give us the ratio of particles on one in the upper energy level versus the lower energy level. All right, so you are going to get a number of particles in the upper energy level, so let's call them NB. So I'll have some atoms which are going to be excited, and some of them which are going to be in the lower energy level. So we could write these things in terms of probabilities, but since this is pre-quantum mechanics, Einstein sort of described this in terms of the number of particles that you have up there or whatever. So, and he postulated the existence of 3 types of processes, okay? Those that are stimulated absorption, okay? So let's look at the rates. So the rate of going from A to B, so this is stimulated absorption. There's going to be some light electromagnetic wave which comes in and excites the atom from A to B, and he called this coefficient B A to B times rho of omega 0. He said it's this process is going to be proportional to the energy density. Okay, so we derived this in quantum mechanics, but it's interesting that Einstein sort of speculated this because, okay, if you have more electromagnetic energy, it's more likely that this process is going to increase. Okay, so he said this has to be proportional to that. There's an opposite process. Okay, so these are the B processes, which corresponds to B to A. So this is stimulated emission. So the system emits some electromagnetic energy and goes to the lower energy state. So this is going to be B to A, and that's rho omega 0. So in our case, we don't have a distinction between these two things. We are looking at a time reversible problem. So the transition rate that I gave you, if I can find it someplace, is going to be actually the same. So our B that we found is equal to pi epsilon 0 h bar squared. Okay, this p squared that you have to calculate, rho omega 0. Okay, so this is our B that we had calculated earlier. Okay, now Einstein also said, okay, there must be some other process, A, okay, which is the spontaneous. So spontaneous means it happens by itself. So even if there's no field, nothing that's influencing anything, you have some rate which he called A rate. Okay, so since he could not relate that to the fields, that just stands alone. Okay, so let's now see what happens when we actually look at the transition rates. Okay, so if I look at the rate of change of numbers of particles in the upper state, that's going to change, okay, according to a master equation. So if you studied the master equation in statistical physics, you know how these things relate to one another. Okay, so the rate of change of NB is going to be proportional to, okay, minus A and B. So if the particle is already in the B state, there's a probability that it will, okay, go to the A state. So that's something that decreases the number of particles there. Then there's going to be this rate, okay, which takes particles from A to B, but that will be proportional to an A. So if the particle is in the A state, with some rate it can go to the B state, and then it can decrease B to A and B. Okay? And, okay, then he said, well, in equilibrium, so when you reach some equilibrium, then this is going to be 0. The number of particles is not going to change. And that's going to be minus A and B plus, okay, in place of RAB, I'm going to put AB, rho omega 0, and A minus B to A and B, okay, rho omega 0. And then he said, okay, let me just derive an expression for rho omega 0. So what's that going to be? It's going to be A and B moving NB to the left-hand side. And then I have, a bunch of terms here. B A to B and A minus B to A and B, okay, is equal to rho omega 0. Okay, so this is the energy density which we have derived in this course, and you probably it's also seen in statistical physics course. But it could also be measured experimentally at the time of Einstein. Okay, so then you divide these things by NB, and you are going to get A divided by B AB and A over NB minus B to A. But this is some factor which we can easily get from statistical physics. Okay, it just depends on the energy levels of the two systems. So this is just equal to e to the B minus EA is larger, so EB minus EA over KBT. Okay. Now, if you look at the actual expression for the energy density in a black body radiation, we know that this is proportional to, okay, so there are certain prefactors which we could write down, but we are running out of time, so I'm not going to discuss that. But this, the omega, the energy density rho omega 0 looks something like 1 over e to the EB minus EA over KBT minus 1. Okay, so this is the black body spectrum. So there's some prefactor, but you have something like that. So Einstein said, if these things are going to be compatible, then this implies that I have first of all, B A to B must be equal to B to A. Okay, so that's a very significant result. We obtained that using quantum mechanics, but this was, obviously earlier than quantum mechanics. And after that, once you get that, then you can just say, you can just make the statement that this is equal to A over B, divided by e to the EB minus EA over KBT minus 1. Okay, so then you try to associate what this factor is with this piece, which is in itself an interesting story, somewhat historical, but you see what's important is you can now associate what this A is, the spontaneous emission rate, to the properties of the heat bath. And one interpretation that you can give to this, is that you can now treat this as a rate, which is going to have some, coefficient multiplied by the energy density associated with the 0 point energy of the system. So the 0 point energy of the black body radiation, so even if you cool it to 0 Kelvin, the remaining fluctuations due to the harmonic oscillator ground state, interacts with the atom to, have this spontaneous emission. Those things cannot be discuss too rigorously at this stage. So that's where we are going to leave it. Okay, so I'll let you go. We'll meet again on Tuesday.